So recently made a video where I analyzed 3 problems from this CodeTON round. But some of you may ask, what about the next 3 problems? Are they so hard that it's no point in even trying to solve them? And my answer is absolutely no. You should always try solving harder problems. Sometimes they require the knowledge of some topic/algorithm which you don't know. When you see it, what you must do is just go and study this topic, or at least write it down to study it in the future. But I know that many of you guys have the opposite problem. You're obsessed with topics, like many of my students are, and you learn stuff that you may never use, like play tree or whatnot, but you don't actually solve the problems that you couldn't solve during the contest. And that's actually the problem that I used to have when I was very good in school Olympiads, and I knew most of the topics that I needed for a CodeTON round, but my rating was relatively low. So what I did is I just started solving 1 or 2 problems that I didn't solve from every contest in which I participated. And my rating went up surprisingly fast. But I didn't just read the solution. You can't just go like, oh, I didn't thought about that, here is how I should have solved it. No, you need to go deeper and ask yourself, why didn't you think about that idea? You have to find the point in your thought process where it went wrong, where you diverted from the right path. Maybe you focused too much on an idea which wasn't going to work. Maybe you ignored some part of the statement which contained a hint. And sometimes the answer will be simply, I just didn't thought about it, and it's fine. What you should do in such case is simply repeat in your head several times the problem statement and the key idea to really build the association in your brain. That in such problems that feature this and that, such construction or such reformulation or such way of thought is sometimes helpful. Or you can go more meta, with the answer to the question what went wrong being simply, I shouldn't have tried to solve this problem, I should have tried this one instead. Or I tried to keep too much stuff in my head at the same time, which led to bugs. But there must be a lesson that you learn from every mistake, and that's what is important. So to give you an example, I will analyze the 2 next problems which I didn't analyze in that video. And I'll start with the problem G because I think it's actually easier than the problem F. The topics that you must know to solve this problem is only the expected value and the modular inverse. But you don't need to know a lot about the expected value. You just need to know the definition. So if you don't know what the expected value is, just go and read the definition. And for the modular inverse, you can read my blog on CodeTON. The link will be in the description. So you can read the statement now or listen to my explanation. In my words, there is an array A of length n that you are going to generate as follows. First, you choose the integer k from 1 to n, and you are going to generate the first k elements of A. The other elements will be 0. And for the first k elements, the ith element will be 1 with probability pi, and negative 1 with probability 1 minus pi. Then you take the maximal prefix sum over all prefixes of that array, including the empty prefix. So the maximum prefix sum will be obviously between 0 and n. You are also given n plus 1 integers h0, h1, etc. hn. If the maximum prefix sum of the array is s, then the score of the array is hs. You need to find the expected value of the score of your array for every possible k. And yes, the statement is a little complicated, but actually it's not that hard to understand if you draw it. So you have n integers. First of all, you pick some k, and you will generate the first k elements of the array. The others will be 0. And for each of those elements, you have a probability with which they are going to be equal to 1. And if they are not going to be 1, they will be negative 1. So some of them turn out to be 1, some of them turn out to be negative 1. Then for the generated array, you find its maximum prefix sum. In this case, the maximum prefix sum is 1. So the score of this array is h1, whatever it is. And h1 is not necessarily larger than h0. So you need to find the expected value of this score. And if you don't know what the expected value is, it's like the arithmetical mean of all the scores that you will get if you generate it 1 billion or 1 trillion times. And it can be expressed with such formula. Sum over all possible scores so this is a possible score, times the probability of such score. Let's denote it with P large S. It's the probability that the score will be HS. So it's the probability that the maximal prefix sum will be equal to S. I will probably make a full video on the topic of expected values, but for now, let's just try to solve this problem. First of all, we need to find the answer for all possible cases. This seems kinda like a random addition to our problem. So let's maybe first try to ignore this constraint and let's just solve this problem when k is equal to n. So we generate the full array. To be honest, I didn't solve this problem on my own, so I will just tell you the main trick. The main trick is to generate the array from right to left, not from left to right. Obviously, it doesn't matter in which order you generate, the expected value will be always the same. If you generate from right to left, you can apply process DP. What is process DP? It's when you generate some objects using a step-by-step process. And you want to find some information about those objects, either their amount or the maximal score of such object. And the score can be defined in any way, it depends on the problem. But in this case, what we want to track is the probability of such path of the process. Optimally, for every possible maximum prefix sum, we want to find the probability of such prefix sum, which is the sum of probabilities over all possible arrays that have such maximum prefix sum. So maybe we can go from right to left and pretend that we generate this array and keep track of some information about the previous steps of this process, which will be our parameters in the DP. And when we arrive to the end, the information that we kept track of should be enough to know the maximum prefix sum. So maybe let's just say that we keep track of this maximum prefix sum over all the values that we already generated. So what is currently the maximum prefix sum? Suppose that currently prefix sum is equal to S. If we add another 1 to the left of our array, the new maximum prefix sum will be S plus 1. But if we add -1, the maximum prefix sum will be either S minus 1, as shown on this image, or just 0 for an empty prefix, if S minus 1 is negative. So we can easily update the maximum prefix sum of our already generated values when we add another value to the left. And I could say that we keep track of the total probability over all processes that arrive into such state. But actually, that's not needed. Let's make it even more simple. Let's say that the parameters of the DP will be I, which shows the last value which I generated, the position of the last value. And it will decrease as we generate new and new values, of course. And the second value is S, current maximum prefix sum. And the value of DP will not be the probability of all processes that arrive into such state. It will be the expected value of the score of the array if we already know that the outcome of the previous steps of the process is this. The current prefix sum is S. Because we understood that this information is enough to know what the S will be equal to in the end if we know the outcome of all those steps. So the value of the DP will be the expected score of the array that can be reached from such state of the process. We know that the process can go only in two other states, either DP I minus 1 S plus 1 or DP I minus 1 maximum of 0 and S minus 1. And we go into such state with probability P I minus 1 and into such state with probability 1 minus P I minus 1. And suppose we already know the expected value of the score of the array in that case and in that case. And guess what? The expected value of the array in our case, in case DPIS, is just P I minus 1 times the expected value in this case plus 1 minus P I minus 1 times the expected value in the second case. This is a property of the expected value which is not hard to prove from the definition of the expected value. So here is a formula how to find dpis in O of 1 if you already know dp for smaller values of the first parameter. And the base states of the dp is when I is equal to 0, it's when we already generated the whole array. So dp0s is obviously just hs. If we know that the maximum prefix sum is currently s, then the score is just hs with probability 1. So I is up to n, s is also up to n, so we've learned to solve this problem in n squared. But wait a second, what about different case, yeah? What about k not equal to n? So suppose we only generate those values, and those are 0, yes? Well, I said that those are 0, but in the original statement they said that those do not exist. I just said that making them 0 is the same as saying that they do not exist. But you know what also be equivalent? If you make them -1, this will be as if they do not exist. I mean, in terms of maximum prefix sum. Such -1s in the end will not affect the maximum prefix sum. So you can just imagine that we've already made n-k steps, and we are currently at position k, and the current maximum prefix sum is 0. What is the expected value of the array that can be generated from this state? Well, it's obviously dp k0. So that's what we need to output. We already solved the full problem. I think that's a beautiful solution that makes this supposedly hard problem very easy. Let's look at the implementation. There's just a modular given in the problem. There's just binary exponentiation, which I need in order to find the modular inverses. And I will find them using this function inv. So I just read the probabilities. They are given in the format of x over y. So in order to find the probability modulo mod, I take x times modulo inverse of y. Then we create the dp. So as I've said, the basic states of the dp are 0i, and it's equal to hi. So I just don't read hi, I instantly read hi into dp0i. And then for all the next layers of the first parameter, I fix the second parameter, and I find dpij using our formula. And then I just output dpi0. That's it. Now let's discuss problem f. In order to solve this problem, you need to know the topic of segment trees. Precisely, you will need segment trees with lazy propagation. You can read it now or listen to my explanation. In my explanation, you're given an array A of length n and a number m. You need to build a tree such that each non-leaf vertex of the tree has exactly m sons. Then you need to place the values from your array A into the leaves of this tree. Then for every leaf you will take the value assigned to it plus its depth. Depth being just the distance to the root. And then you find the maximal of such values. You want to minimize this value. So you want the maximum of such values to be as small as possible. But that's not all, because you are also given q queries. Each query just changes one element of A to some other value. You need to output the answer to the problem after each update. So just for example, if m is equal to 3 and the values are 1, 1, 2, 2, 3, what I can do is I can build such tree. Every non-leaf vertex has exactly 3 sons. Now the aforementioned value of this leaf is 1 plus 2, it's 3. For this leaf it's also 3. For this leaf it's 4. For this leaf it's 3. And for this leaf it's 4. So the maximum of such values is 4. And I suppose this is the smallest value you can get for such an array. So the answer for such array would be 4. So my mistake during the contest is that I fixated too much on the idea of the greedy solution. I said that each time we take m of our values and replace them with the largest of them plus 1. So those will be replaced with number 3. And then we sort those once again and take m smallest values and replace them with the largest of them plus 1. In this case it will be 4. And this will be the answer to the problem. So I've managed to prove such greedy algorithm that will find the answer, but it does not lead anywhere. And actually this was a completely wrong path of the solution, because I was thinking about building this tree from bottom to top. You see, I've taken those 3 values and united them into one vertex, and then I take this vertex and those 2 new values to unite them into one new vertex. Well, the correct approach was to generate this tree from top to bottom, and this will be much easier and more obvious. But to implement this approach, you need to first fix x, which is the desired answer. So this approach will not give us the answer, but it will test for a given x if it's possible to make the tree with the price of x or less. So if we know that the price of the tree must be no more than x, we know that the maximum depth of this value is no more than x minus 1. And the maximum depth of this value must be no more than x minus 1. For this value, its depth can be no more than x minus 2. The depth of this value can be no more than x minus 2, and the depth of this value can be no more than x minus 3. So let's now consider those values. Those are just maximal depths allowed for every of your leaves. So 2 of the leaves must be on the depth no more than x minus 1. 2 of the leaves must be on depth no more than x minus 2, and 1 leaf must be on depth no more than x minus 3. It's easier to show the process with a fixed x, so let's check x equal to 4. In this case, those allowed depths will be 3, 3, 2, 2, 1. So how do we build the tree with such depths? We start with the root, and it has m children. And we see that one of the leaves is allowed to only have depth 1. So let's say that this is the leaf. And for the other vertices, let's draw m sons to each of those vertices. Now we see that 2 of the leaves can have the depth at both 2, so we'll have to stop them now. For the other 4 vertices, let's add m new sons to each of them. So 2 of the leaves can have the depth of no more than 3, so let's say those are those 2 leaves. And now we see that we don't need all those vertices. So we have some vacant space here. We can place 10 other values here, but we don't need to. So we can always just delete those unnecessary leaves that we have. And here I will just delete those, but I will just reassign this value to this leaf and this value to this leaf. Because this value was allowed to have depth no more than 3. So if it will be depth 2, it's also okay. And this will be depth 1, which is also okay. So after we generated the tree, and if we have vacant places, we just start deleting m leaves and adding 1 new leaf until we have exactly the amount of leaves that we want. And then we just reassign the values in those leaves that were deleted to some new leaves that appeared after we deleted some other leaves. And their depth will be no more than before. If you, of course, start deleting the leaves from the deepest up. By the way, n is equal to 1 modulo m minus 1, which is stored in the statement. So when we will be deleting m leaves and add 1 new, we'll decrease number of leaves by m minus 1, and so we'll get exactly n at some point. So the key moment that you must understand about this problem is that you don't need to worry about the vacant places in your tree. If you manage to build a tree which fits your values and some additional values, then you can modify it so it suits just your values. And if we don't care about those vacant places in the end, then of course we want to stop every branch of the tree as late as possible. So we only assign a leaf to a value if it has exactly the maximum depth allowed for this value. So when we're building the tree, it's kind of like also a process with 2 parameters. First is the current layer, the depth on which we are now. And the second parameter is just how many vacant leaves do we still have, how many branches are still growing. For example, in this case, we are in the state 3, 10. Because we are at depth 3, and we have 10 branches that are going to grow on the next layer. So when we go to the next layer, there will be now 30 of those vacant leaves. But suppose we also had 3 values 0 here, which became values 4 here. In this case, we'll also have to subtract 3 from the number of vacant spaces after we'll multiply it by m, because we'll have to use 3 of those vacant spaces to place our values of 0 there. And the only way that the answer can be no, such x is not reachable, if we don't have enough empty space for all the values that we have. So for example, if there would be 35 values of 0 here, and I only have 30 vacant spaces, well, of course, I can't reach the answer 4 then. Such x is unreachable. I have to try to build a tree with a higher price. So let's once again have an attentive look on how we check a specific x. Let's look at this process in terms of arithmetical operations. What we did is we started with 1 vacant space. Then we multiplied by m and subtracted f x minus 1 from it, where f x minus 1 is the number of occurrences of the value x minus 1 in our original array A. Because all the values of A that used to be x minus 1 will turn into a maximal allowed distance of 1. So the number of leaves that we'll need to end on the layer 1 is f x minus 1. Then we multiplied it by m again and subtracted f x minus 2 analogously. Then we multiplied it by m again and subtracted f x minus 3 and so on. If you open the brackets, you will get m cubed minus f x minus 1 m squared minus f x minus 2 m minus f x minus 3. And to be precise, I actually had to subtract f x here because in the problem n can be 1, so it's possible to build a tree with just 1 vertex. So it's possible to stop some branch at layer 0. So we also need to analyze such case. And if I add it into consideration, well, I have to add it here, of course, here, 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 but in the end I will get such formula. This is the formula for the number of vacant places that I will have on the third step. So obviously on the last step I will have this many vacant places, m to the power of x minus fx m to x minus f x minus 1 m to x minus 1 minus etc. f1m minus f0. This is the number of vacant spaces I will have at the very end, if the process goes correctly. But how can we know that the process went incorrectly? It's if on some step this value was negative. But if this value is negative, then the final value will also be negative. Because each time we took a value, multiplied it by m, and subtracted some non-negative number from it. If a number was negative, you multiply it by m, it's still negative. You subtract a non-negative number, it's still negative. So if a number is negative, it will be negative up to the very end. So it's enough to just check that this is non-negative in the end. If this is non-negative in the end, the process ended correctly. Now let's rewrite this statement. It's m to the x larger or equal to sum for all I from 0 to x fi times m to the power of I. But what's fi? It's just the number of times the value I occurred in our array. So we can rewrite it as follows. For all I from 0 to n minus 1, m to the power of ai. So this is much nicer because now we are getting close to understanding how we can answer those queries when we change just one I, because we don't need to keep track of those f in fact. when we change an a, we simply need to update this sum. And I remind you, our goal is to find the minimal integer x for which it is true. But this sum can be extremely large, right? Because a can be up to 200,000. So let's instead store this sum as a long integer base m. Let's say this is a long integer base m. And let's say m is 3, for example. When we add m to the power of ai, we simply add 1, 0, 0, 0, 0 in such notation. So we simply need to add 1 here. So I need to just implement the addition of 1 to one of the digits of a long integer base m. And I also need to implement the subtraction of 1 from one digit of a long number base m. I need to implement the subtraction because when I update one of the values a, I have to subtract m to the power of the old value of aj, let's say. And I need to add m to the power of the new value of aj instead. So okay, suppose I've learned to maintain this long number in such notation. How do I find x? So x is just basically the smallest number of zeros that I should write after a 1, so that such number is larger or equal than my number. So obviously this is just equal to the position of the largest non-zero digit if you go from right to left, plus 1. Except for the case when your number is 1, 0, 0, 0, 0. In this case, it's just the position of this last digit from right to left. But I don't want to deal with that case, so I instead subtract 1 from this sum when I check for x. And I say that I want such x that this is strictly larger than that sum minus 1. In that case, I can just take the position of the largest non-zero digit from right to left in this number. But the question is just how to maintain the long number, because suppose my m is 3, right? If I want to add 1 somewhere, if this digit is 0 or 1, I just increase this digit and that's it. But if it's 2, I need to turn it to 1, but carry the addition to the next position. Then if on that position the digit is 0 or 1, I just add 1 to it. But if it's 2, I have to make it 0 and carry the addition to the next position, and so on. So the overall process can be described as follows. Starting from this position to the left, find the first digit, which is not m minus 1. Add 1 to this digit, and turn all those digits to 0. And subtracting 1 works in a similar manner. Starting from this position to the left, find the first digit which is not 0. Subtract 1 from this digit and change all those digits to m minus 1. And finally, to find the price of the tree, after each update we need to find the last digit from right to left which is not 0. In order to do all that, we will need a segment tree that allows such operation. Set value on a segment and find the first position starting from here to the left which is not 0, and find the first position from here to the left which is not m minus 1. And finally, to find the middle price, find the first position from left to right which is not 0. Let's look at the implementation. So in order to quickly find the first position which is not 0 or which is not m minus 1 and so on, I will keep track of the minimal value in each vertex of the segment tree and the maximal value in each vertex of the segment tree. And also I need a buffer for each vertex of the segment tree for the buffered operations of set value on the segment. First of all, write give buffer to the children. I see if I don't have a buffered operation, then I return. If I have a buffered operation, I see if I have children, then I give a buffered operation to them, and I update minimum maximum value. Now it's just this value which I set on this whole segment, and then I clear the buffer. Then set segment. It takes the index of the vertex, the span of this vertex in the segment tree, the semi-interval, and the value that I want to set on this semi-interval. First of all, I call for div to clear the buffer. Then if the span of the vertex does not intersect with the query, then I return. Then if the query totally occupies the vertex, I put buffer into this vertex, and then I instantly clear the buffer, give it to children, because I don't want to leave the incorrect value of minimum and maximum in the vertex when I return from setSeg. You'll see why in a couple of seconds. In all other cases, I recursively call for setSegment in both sons, but then I want to recalculate the minimum value of v and the maximum value of v, using the value in the sons. That's why I didn't want to leave an incorrect value of minimum and maximum when I return from setSeg. Then find rightmost node 9. It accepts vertex and the span of this vertex and the position r large. And it finds the rightmost position of a non-9 digit starting from r large to the left. And by 9, I mean m-1 actually. First of all, when I'm in a vertex, I clear the buffer, then I see if this vertex is totally to the right of this position r, or the minimal value on this vertex is m-1. So if minimal value in this vertex is m-1, it means all the values are m-1. There is no value which is not m-1. That's why I return -1. Then I check if this vertex is a leaf. It means that I've descended into the very rightmost position, which contains non-m-1. And so return the position which this vertex is responsible for. It's L. Otherwise, I first try to call for the right son, but if it returned -1, then I call for the left son. I similarly implement the functions find rightmost non-zero and find leftmost non-zero. You can read it yourself. It's analogous to the previous function. Add elements is needed to add x to one of the digits. It does not concern carrying to other positions. It just changes the value of one digit. So it accepts a vertex, the span of this vertex, then the position, and the value which I want to add. It can be 1 or -1. I clear the buffer. I see if I'm in a leaf, then I need to add x here. So I add it to minimum and maximum. And I return. Otherwise, I see in which of the sons I need to descend. I descend into that son, but I clear the buffer from the other son because I want to update min of v and max of v. So I want the values of minimum and maximum in both of the sons to be correct. That's why I clear the buffer in both of the sons manually. And finally, the function add adds 1 to the ith digit, but now with carrying. First of all, my digits are numbered from left to right, and add accepts the position of the digit from right to left. That's why I transform I to len -1 minus I. Len is the length of my number. I fix it in the very beginning and then don't change it. So L is the rightmost non-9 starting from this position to the left. I add 1 to that position L, and then on the whole semi-interval from L plus 1 to I plus 1, I set all the digits to 0. Del works similarly, as you see. The only difference is that it finds the first non-zero starting from this position to the left, adds -1 there, and sets all the digits from L plus 1 to I plus 1 non-inclusively to m-1. And the main function is really short. I just read nmq. Then I set the length of my number to be n plus 20. Why n plus 20 is because if every value which I will add is m to the power of n, then it's like adding 1 to the nth digit from right to left. If I add 1 to that digit n times, it can be carried to larger positions. But the furthest it can be carried away is log n base m. So it's, in the worst scenario, base 2, which is around 17, 18, something like that, if n is no more than 200,000. But I add 20 to be sure. Then I find the tree size, which is just the first power of 2, which is larger or equal than 2 times length. It's the number of vertices which I need to allocate for the segment tree if I want the root to be responsible for the segment of length len. Then I allocate the segment tree. Initially, all the digits are 0 and all the buffers are empty. When I read AI, I instantly want to add m to the power of AI to the sum. That's why I call add AI. And then, q times, I read the query, I change the value of AI, That's why I first delete m to the power of ai. From the sum, change the value and add the new m to the power of ai. But then you remember I wanted to subtract 1 from my sum. That's why I call del 0. It effectively subtracts m to the power of 0. And then I add m to the power of 0 back, which is 1. And in the meantime, I find the leftmost non-zero, which is just the highest digit of that number. And remember that my digits are numbered from left to right, so to flip it, I need to output len minus this position. You can safely subtract 1 here, because our sum is always positive at this place. That's it for today. Thank you for watching, and I remind you that I give private lessons on competitive programming. If you are interested, contact me on Telegram. Goodbye.